last session we stopped here, and the idea was we want to improve the performance of Wasserstein GANs. And if you compare GANs to Wasserstein GANs, the only difference is that you're going to notice in the objective function is that you are getting rid of these log terms. There's going to be a minus here, which is going to correspond to the minus over there. And then at the same time, your discriminator, you're going to call it a critic, because whatever that's coming out of your discriminator or critic is no longer getting pushed through a sigmoid function. So you get rid of sigmoid, you get rid of log, and then that's going to give you the objective of Wasserstein GAN. But then there's a catch. We need some nice properties out of our critic for us to be able to draw the analogy between minimizing and maximizing this objective function and minimizing the Earth mover distance. And those nice properties is basically the critic being Lipschitz continuous. We saw some methods of enforcing that, which was a little bit ad hoc. You needed to play around with your training process, that whenever a weight throughout the training is going to exit a box, you're going to clip it inside the box. Another solution is using the gradient penalty, which is based on this nice theorem that if a differentiable function is one Lipschitz, then its gradients are going to have a norm that are at most one everywhere. And this is not only one-sided, you can also go the reverse route. So it's a two-sided statement. If you have a differentiable function whose gradients have a norm that is at most one, then it's going to end up being Lipschitz. And then you can add the gradient penalty. You don't want the gradients of your critic to become too big or deviate too much from one. And equivalently here, you can have a hinge type of a function so that you always make sure that the norm of your critic is less than one. But then the other key statement in that theorem is everywhere. You are not going to be able to span the entire space of images. So you are not going to be able to satisfy this everywhere. Perhaps while you are generating images and looking at your real data, perhaps you can look at one point on the line between the two and try to enforce this gradient penalty on that line. And then this way you're going to try to enforce Lipschitz continuity. But then the problem is you're introducing a new hyperparameter, and then you have to keep adjusting it to give you high quality images. And we know that one way to do that, to set those hyperparameters, is to look at the performance metric on a bunch of validation data. And the validation data, you can set aside a portion of your data, that's fine. But then what is your metric? Perhaps you can use inception metric here, or inception distance, and try to set this hyperparameter accordingly. Any questions so far about gradient penalty? Was everything clear? Okay, perfect.